Hello and welcome back again to our channel, and today we're going to be looking at indices and logarithm. We're going to do a comprehensive lecture. I know we have previous videos on various different sections of each of these topics, but I thought of bringing everything together so that when it's your go get to lecture, so that you can have everything in there, have everything in there. I hope each and every one of you is doing well. If you haven't yet subscribed to our channel, please do us a favor by subscribing so that we can be able to grow this channel as a family together. Today, we're looking at indices and logarithm as a comprehensive lecture. Now, when you have it's usually of the form maybe a, and then there's a power. There's a power like n. There's a power like that. Now, indices was invented by Samuel Jeek. It was invented by, let me write it on the side here. So indices, propounded. It was propounded by Samuel Jeek in the year 1696. In the year 1696. So we are saying that normally with indices you'll see something like this, and this is usually called the base. It's usually called the base, and then the one on top here is known as the power, or some books will say exponent. The exponent. So whenever you see something of this form, then you know you are dealing with what? You are dealing with indices. You are dealing with indices. So we'll be looking at some of the properties of indices. So if we want to look at this number, maybe one, for example, we want to look at one, for example, we can write one as an indices or as an index in terms of 1 to the power of 0, because we say that any number, any number any number raised to the power of 0, raised to the power raised to the power of 0 will give you 1. So basically what you are saying is that if you have if you have a million, I can't even write a million. Can you imagine? Imagine you have a million all raised to the power of 0. We are saying that this is equal to 1. We are saying that this is equal to 1. So we can write 1 as an expressive form of 1 to the power of 0, which is 1. Or we can also write the same one, we can write the same one as maybe 1 to the power of 1. The same one as 1 to the power. So if we write 1 as to the power of 1, or we write to the power of 0, it's the same thing. And we've been able to express these two. All that, these two, as what? An index. We've expressed in terms of indices. We've done an indices with that. So now let's look at some of the properties of indices. Let's look at some of the properties. So like we said that if you have maybe a, it can be written as maybe a to the power of n. We also have, let's say, if you have a to the power of 0, we say it's equal to 1. So example, we give an example and we say that an example is if you have maybe 1 to the power of 0, or you have 100 to the power of 0, or you have maybe negative 5 to the power of 0. We are saying they are all equal to 1. That's what we are saying. Now another property another property that we have is that we're saying that if you have a to the power of m and you are multiplying, sometimes in indices multiplication is a dot like this. It's different from the decimal point. And you also have another a to the power of n. We're saying that this is going to be the same as a to the power m plus n. Now we need to be very careful. We need to be very, very, very careful here. We need to make sure that this base, all right, is equal to this base here. They should be the same. And if they are the same, and then there's also supposed to be a multiplication sign here. Once you have the bases to be the same and there's a multiplication sign in the middle, we can now add the exponent. So we are saying that an example, let's look at an example. An example of that is if you have, let's say, 5 to the power of negative 2, and we are multiplying it by 5 to the power of, let's say, 4, we are saying that because this 5, this base, is the same as this base. You can see it's 5 and 5. And then in the middle, we have a multiplication sign. It means we can add. It means we can add the exponent. We can add the exponent by having 5 whole number negative 2 plus 4. And when we do that, remember, we said negative 2 is when you owe. You owe someone. And then the plus 4 is you have it in your wallet. This is in your wallet, $1. You have $4 in your wallet and you owe negative $2. So what it means is that when we pay the owner, the one we are owing the 2, he has to give us change back. We need to get a change back into our wallet, which is $2. And because it's ours, that becomes positive. So we're going to have 5 whole number, 4 minus 2, which is basically 5 to the power 2. And there you have it. Now the next property we're going to have is similar, but it's a little different. Imagine we have a to the power of m, and this time we are dividing by a to the power of n. We are dividing by a to the power of n. We're saying that that's going to be the same thing as a to the power of m divided. You can see it in different forms. It could be this form. We're saying that this form is the same thing. This form here is the same as that. They are the same. They are the same. Because what we have in the middle here is division. There's also division right here. And we are saying that once we have that, we're going to have a to the power m minus n because the b's are the same and they are dividing. So we want to make sure. So an example of that is, let's say we have the same, maybe 5 to the power of negative 2, and we are dividing by 5 to the power of 4. We are saying that it's going to be the same as 5 to the power of negative 2 divided by 5 to the power of 4. And we say that because the bases are the same, we subtract. So we get minus 2 minus the 4. And then we end up getting, what do we get? Is anybody ahead of the class? We're going to get 5 to the power of negative 6. 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 Now let's look at another property. Another property says that if we have a to the power of negative m, we're saying that write 1 in the numerator and divide it by the denominator. By this time it's going to be positive. The negative that is here is gone because we put a 1 here and divided by that same thing. So let me write this thing well. Doesn't look pretty. Doesn't look pretty. So now we have a to the power of m. We are saying that it's the same thing as what? It's the same as an example. Let's say we have 5 to the power of negative 2. We are saying that always write 1 and divide by the positive of the exponent, like that. We're going to get 1 over 25. But we know 5 squared is the same as 5 squared. Sorry about it. 5 squared is the same as 5 times 5, and then we get 25. All right. So those are the properties that we have so far. Now we're going to continue. We're continuing some of the properties. We're going to continue properties of indices, and we say we are continuing. It's continued. So we have the next one. We said that if you have a, and use a blue and be consistent. Let's say we have the a to the power of n, or let's say to the power of m, or into parentheses n. We're saying that this is the same. It's the same thing as the a to the power of m times n. Anytime we see something like this is what we do, which is the same as a to the power mn. So we don't have to forget that. Please, let's keep that in mind, please. The next property says that if you have a divided by b all to the power of, let's say, m, we are saying that it's the same as taking the a to the power of m and dividing by the b to the power of m, like that. A to the power of m divided by the b to the power of m. A to the power of m divided by the b to the power of m. Okay, so let's don't forget about that. Now let's say that we also have a little change here. We are having, let's say, a divided by b, but this time to the power of negative n. It's a negative here. What do we do? They said the rule says that we should change it. We should make the b, the denominator, come to the numerator. So the b goes up, the numerator goes down, and then we can have this as positive n. And then from there we can apply. We can apply this property here. We can apply this. So the top is going to be b to the power of n divided by a to the power of n. Divided by a to the power of n. We're applying this property here. This property here rather, instead of the first one. So we're applying right there. So we're applying right there. Now, the next one is, if you have, we have, let's say an index on the left side, but there's an equal to sign in the middle of another index like this. Now remember, you see this a here, the base here, and then the base here, they are the same. They're the same, and because they're the same, and we also have what, an equal to sign in the middle, it means that the m should also be equal to n. The exponents are the same. The exponents to are same. Exponents to are same. So let's look at a situation. Let me give examples. Let's say that for this one here, we have, let's say, 2 to the power of 3, and we are to the power of negative 4. We're saying that it's the same as 2 to the power of 3 times the negative 4. We get 2 to the power of negative 12. Here, which is the same as what? Can you be able to do that? It's going to be 1 divided by the 2 to the power of 12. Don't forget that. Now here too, we are also having, let's say, 2 to the divided by 5 to the power of 2. We said it's the same as 2 to the power of 2 divided by 5 to the power of 2. Don't forget that. The exponent applies to each of the fraction there, each of the numerator and denominator. Sorry about that. And we're going to get 4 over 25. Now the next thing is, let's imagine we have 4 over 7 to the power of negative. We are trying to apply the properties that we went through to the power of negative 3. We are saying that let the 7 go up, let the 4 come down, and then bring your 3 on top. And that gives you 7 to the power of 3 divided 4 to the power of 3. And then we take it from there. Also, here, let's imagine that we have x to the power y, and we are saying it's also equal to x to the power negative 2y, for example. Now we are saying that because this x is the same, they are same. They are same, and what is in the middle is equal to sign, not a multiplication. If it's an equal to sign, then since they are the same, then it means the exponents are also same. So we are saying that y should be equal to negative 2y, and we're going to get y plus 2y is 0, and we get 3y is 0, and y is 0. All right. So that's where we are currently. We've looked at the properties of indices. Now, sometimes I want you to do something again. Sometimes it depends. We can have what we call exponential functions, where we can have maybe exponential. We have some exponential functions, and how we can apply indices to it. Indices application. Let me put it that way. So let's imagine that we have we know that exponential function is of the form e to the power of what, m. You're always going to have an e. An exponential function is always going to have an e. Always. The e is always present. That makes it an exponential function, and it's going to have what? A power. It's also going to have a power or an exponent. It's going to have a power or an exponent. So we can apply. We can take some of the properties. We said that if you have e to the power of 0, we'd say that it's equal to 1, because e is also anything e. Anything to the power of 0 is 1. If you also have e to the power of 1, we're saying that it's going to be the same thing, e itself. If we have e to the power of a multiplying e to the power of b, we're saying it's the same as e to the power of a plus b. Remember, we said that. An example, let's say you have e to the power of 2 multiplying e to the power of negative 3. We said that because e and e are the same and we are multiplying, we add the top. So it's going to be e to the power of 2 plus negative 3, which is 2 minus 3. And we get e to the power of negative 1, which is 1 over e to the power 1, which is 1 over e, which is 1 over e, actually. So we can apply. I'm just saying that we can apply all that we've learned. A divided by eb, we're saying the same as ea over eb, and we are going to get e to the power a minus b. That's all we are saying. If we have, we're saying that if you have e to the power a to the power m, we're going to get e to the power a times m, which is am. We're going to apply all. So all the things that we have learned about indices can be applied to exponential functions. I'm mentioning this so that when we get to exponential functions, you will not be caught. You feel different. That this is the first time it's been introduced. So that is the indices for you. That is indices for you, and I would like to see if we can take some maybe question. Let's do one question on indices, and we can move on to logarithms. So the first question there, the first question says, let's say we have 9 to the power negative half. It's equal to 27 to the power 1/4, and we are dividing that by 3 to the power, I think, x plus 1. 3 to the power, I think, x plus 1, like that. So let's look at what we're going to do. Now, if you look carefully, if we look at this 9 and look at 27, look at 3, there is something common about them. There's a common number, and that common number is 3. That common number is, so to write 9 in terms of 3 is 3 to the power of 2. It gives us 9 because the common number between all of them is 3. So we are going to write everything, we're going to express or write everything in terms of 3. And to do that, 9 gives us 3 to the power of 2. And remember, there was something already there, which was negative half. Because what is inside now is just a 9. That's all we've done. We've not done anything special. It's going to be equal to the 27. It's also going to be 3 to the power of 3. And there is something also on top, which is 1/4. And then we have divided by 3 to the power x plus 1. 3 to the power x plus 1. Now we're going to be able to expand the top, and we are going to get 3 to the power 2 times negative half is equal to 3 to the power 3 times 1/4 divided by 3 to the power x plus 1. Now we're going to get 3, and this cancels, and we're going to get negative 1. It's going to be 3 to the power 3/4. Why? Because there's no common factor on top there. Divided by 3 to the power x plus 1. Okay? 3 to 1. Now let's do the right hand side. This is the right hand side. There's division that we can be able to do something about it. Remember, we said if you have a to the power m divided by a to the power n, this is the same, and this division is going to be a to the power n minus n. Please do not throw the rules away. We need the rules to be able to solve the problem. So we are going to have 3 here to the power 3/4 minus x plus 1. All right? And then here 2 becomes 3 to the power negative 1. We know that the 3 to the power negative can be written as 1 divided by 3 to the power 1, which is the same as 3 whole number, 3/4 minus x minus 1, like this. So we don't even need to even change anything. We're writing everything in terms of 3. So here's 3 to the power negative 1. Now remember this rule. We said that if you have a to the power m and there's an equal to sign separating the same base and a different exponent, we're saying that then the m is equal to the exponents are the same. The same thing is happening here. This 3 is the same as this 3. It means the exponents should also be the same. So we're going to have negative 1 is equal to 3/4 minus x minus 1. Minus x, and then we are looking for x. And since we are looking for x, we can make this negative 1 be here, and then this one cross to this side. So that will be plus 1, and then this one too is going to cross. So it becomes minus 3/4 is equal to negative x. Is equal to negative x. And then now we know this, and this will go to 0. Minus 3/4 is just negative x. So we're going to have 3/4 is equal to x. Therefore, x is equal to 3/4. It's equal to 3/4. So I think the year ends. We end the indices side of things, and we now go into what we call logarithms. We go into the logarithm part. Logarithm part. So logarithm was also invented or propounded by John Napier. So we have logarithms. Logarithms was propounded by John Napier. Propounded by, sorry, I think, let me see. Propounded by John Napier. Yes. And now, how do we know a log? So let's imagine for a second, a log is expressed in this form. It's of the form log, let's say log b to the base a. So we have a log b to the base a, and we are seeing that this a here is normally called the base, and then this is the result. Okay, this is the result. This is basically the results Okay, it's called the result. Just like we have that index. Remember the index form, indices form. We said that indices form is a to the power of, I think, let's say n, and we said that the a is this one here, is the base. Well, this is the base. This is called the base. So that a is the base, and then the n there is the power. Then there is the power. So we are going to look at a few. If another thing, if you also have a logarithm of the form, maybe log 3. What it means is that we are working with base, in base 10, even if not stated, So if we write a log, let's say we write log 20, it means we are working in log 10. If we write log, let's say 5, it means we are working in log 10. So I just wanted to keep that at the back of our minds as we continue this journey, together. Okay, sorry about that. As we continue this journey together. So we've looked at the one who propounded logarithm, which is John Napier, as of the form log b to the base a. The a is the base and the b is the result. And then we said that if a log is written without the base, it means you are working. It's automatically working in base 10. We are working in base 10. Now, how do we evaluate a log? Evaluate a log? So let's say that we're still with the same, let's say, log b, right? And then base a. How do we evaluate this? So to evaluate this, we normally will have something like log b to the base a. We equate it to x. We equate it to x because we want to evaluate it. And to do that, we know that this base, because this is the base, it will be of the form the base to the power of x. The base to the power of x. Because we said that x is here, it will become the what? X is the power. And then we said the b is the what? The result. So x gets goes to top of the base a, and it's going to be equal to b. So let's keep that at the back of our minds, and we're going to start another property. It says that if you have log, I think I'll start that as the property. So let's say properties. Let me write that down. Properties of logarithm. Properties and laws of logarithm. Yeah, logarithm. So the first one, we are saying that if you're having a log 1, now here there's no base, so it means you're in base 10. It means is equal to 0. The second thing is we said that if we have log and of the same base, the base and the result are the same, it means it's equal to 1. It's equal to 1. So let's keep that in the back of our mind. So for example, we are saying that if you have log 3, sorry, if you have log 1, we're saying that if you have log 1, whether the base is 100 or not, is 0. Is 0. Whether the base is 1 million, once it's log 1 to the base anything, the base is anything but it's log 1, is 0. Is 0. Now, we said that how do we evaluate? Remember, we said how do we evaluate? We said that if you have log, sorry, let me use a different ink, maybe blue. Take a blue. We said that when you have a log, right? When we have a log, what am I writing? What am I writing? We said if you have a log, maybe log b to the a. We said that to evaluate it is log b to a is equal to x. And then we have to take the base to the power is equal to b. Remember that's what we indicated. So what it means is that we can apply this rule, the evaluation here. What it means is that because we have this, the 100 here will be the base to the power 0. We are saying that is equal to 1. Yes, that's equal to 1. So don't forget that. That's what we stated to be a property. That if you have log 1 is 0, and we are proving it. How to be able to arrive at this. Now here too, because we are evaluating the a will be the base and then the 1 becomes the result, which is the power. So it's going to be a whole number to the power of, let's say, 1 is equal to a. Okay, it's equal to a. So those are the, should I say, first two maybe properties. And then the third one, maybe the third property is the law. It says that if you have log AB, log of AB. Now remember, there's no base we've written. That means you're working in base 10. Don't forget that. Log of AB is equal to log A. It's equal to log A plus log B. Please, we are not saying that log A times log B. We know, say the log of A and B. So we are not looking at this. If in case you're looking at log A times log B, no, it's wrong. They're not the same. Okay, they're not the same at all. So the first log of AB is not the same as log A times log B. They're not the same. They're not the same. So if let's say we have we have log 6. Okay, we can write this log 6. We can write this log 6 as log into or 2 times 3. This is like the A, and this is the B. And the moment we have that, we're going to have log 2, but this is log 2, log A, log 2, plus log 3, plus log 3, plus log 3. The next one, and to prove this, okay, let's quickly look at the proof. We know that log AB, we said log of AB is log A plus log B, not times. Now we can say that, let's equate this to be equal to a certain number. Let it also be equal to a certain variable. Maybe this is y and this may be x. Okay, so what it will mean is, because we have log A to be x, it means that this base, which is 10 to the power x, is equal to A. All right. What about this side? If we also have log B equal to y, you're going to take the base, which is 10 to the power y, is equal to b. Now we're going to multiply these two. We multiply these two. We multiply them together, and to do that, we're going to get 10x multiplied by 10 multiplied by 10y, and it's equal to what? A and b. Go to A times b. Okay. Yeah, we are looking at how we can be able to multiply them together. Now here, because the bases are the same, we add the top. It's going to be 10 to the power x plus y is equal to ab. And when you take the log of both sides, the answer comes out cleanly. Now you take the log of this and log of that. We're going to have another law. This x plus y is going to drop. So it's going to be x plus y log 10 is equal to log AB. It's equal to log AB. And to be able to achieve that, we know that our x plus y, because log 10 is 1, because log 10 is 1, y was log, yeah. So we're going to get log 10 to be equal to 1. Yes. And once that one is 1, this is what we are going to get. We are going to get x plus y, which was log 10, is equal to what? Log AB, right? Log AB. And this, we said this is 1. Multiplying x plus y is equal to log AB. So now we have log AB is equal to x plus y. And we know this x is log A. And then this b is log B. Yeah. So I hope this proof clarifies where we are getting this particular formula. Okay, I hope it clarifies where we are getting this formula. All right. Now let's look at the fourth maybe property, or should I say law? Yeah. So we said that we are continuing with with the second property, which is log. Log A over B we said is the same as log A minus log B. Now remember, we're saying that this log A over B, it is not the same as log A of itself divided by log B. It's not true. It's not true. So let's be careful. So we're saying that log of A over B is equal to log A minus log B. So that's when it will work. Now, how do we prove this? Same thing. We are going to make this one to equal to x and make this one equal to y. So it means you have log A is equal to x, and you also have log B is equal to y. Now, what we do? We know that because we are not written in the base, we're working in base 10. So that's going to give us 10x is equal to A. And it's also going to give us 10 to the power y is equal to B. Yeah, we're able to get this for a starter. Then we multiply. Yeah, we multiply the two. So what do? We have 10 to the power x times 10 to the power y is equal to A times B. Now, because the bases are the same, we add the top. So it's going to be 10 to the power x plus y is equal to AB. Now, we're going to take the log of both sides. Take log 10 to the power x plus y is equal to log AB. And then we're going to get x plus y is equal to x plus y times log 10 is equal to log AB. Equal to log AB. Equal to log. Did I say we're going to multiply? No, we're going to divide. Sorry about that. We're going to divide. Sorry about that, please forgive me. We're going to divide. That's the main thing. We're going to divide the two. We're going to divide. And to divide, we're going to get 10x divided by 10y is equal to A divided by B. And because the bases are the same, we're going to get 10 to the power x minus y is equal to A divided by B. We take log of both sides. We're going to get log 10. Log 10 to the power of x minus y is equal to log of A over B. Yes, and then we know that our x minus y will drop. X minus y log 10. Yeah, x minus y log 10 is equal to log A divided by B. And then we can be able to do a trace right here. So we have x minus y log 10 is equal to log A over B. Yeah, log A over B. And then we know that our log 10 is 1. Why do we know it's 1? Because the base here is not written, but we know we are working with base 10. So if the base are the same, if the base is the same as the exponent, which is log 10, is going to be 1. And then we have our x minus y here, which is equal to log of A divided by B. Now we're going to have x minus y is equal to log A divided by B. Therefore, log A divided by B is equal to x minus y. Is equal to x minus y. And we've been able to solve it because our x there, our x here, I don't know what I can say. Our x here is what we got here, we put here. This is our x is log A minus our y is log B. Okay, so therefore log of A divided by B is equal to log A minus log B. I hope that works. Now another property says that if you have log A to the power n, we say that we should drop the n. The n comes down, and then we get log A. The n comes down, we get log A. We also said that if you have log A to the base A, we say it's equal to 1. So if you have log, let's say 1,000, and the base is also 1,000, it's going to be 1 because the bases are what? They are the same. The last property we are going to introduce, and maybe do some question or problem, is we want to change the base. We want to change the base of a logarithm. Okay, it's very easy. If let's assume that we have log 5 to the base 2. I want to change this want to change to base 4. We are saying that the trick here is that if you look at this, the 2 is below, right? 2 is down here. And so we have 5 is top. Can you see that? And 2 is below. So to be able to change the base to 4, we're going to write the log of the top divided by log of the bottom, of the below. And then the base here will be what we want. Okay? So log of the top is log 5. Yes. It's log 5. And then the bottom is going to be log 2. But the base is going to be 4 and 4. And guess what? We are done with changing the base. So if, let's say, let me take another example. Let's say we have log 7, 3. And I want to change it to what? Base, let's say 6. I'm going to have the top. This is the top part. Log 7 divided by log what? 3. And I put what? The 6 down in the base is right there. And then I think we are done. Now let's look at maybe if there's a problem. Let's look at maybe let's look at an indices problem or something. Okay, sorry, a logarithm problem, and let's see whether it can do us some good. Okay, let's see what I can do us some good. So let's say that I have a question here. Let's say that we have a question that says x is equal to 2 to the power of p. And then we also have y is equal to 4 to the power of q. Now they wanted to show clearly, that if you have the log of x cubed y to the base 2, that is going to be the same thing as 3p, 3p plus 2q, plus 2q. So now remember, our x is 2p. Our x is 2p. So we can easily plug in things here. Now we have 3 and our p there is what? Well, we don't know what our p is, but we know what x is. So let's start from the left hand side. But we've been given what x and y is, so we can be able to work from there. So yeah, it's going to be log, so base 2, and then the x there, this x here, is 2p, 2 to the power of p, right? This is our x, and that x is the power of 3. And then the y there, the y is 4 number to the power of q. Yeah, to the power of q. And then we would have represented that particular side of the logarithm. So we have s cubed y. And the s cubed is 2 to the power of p. Yeah, it's 2 to the power of p cube. And then multiply by y, which is 4 to the power of q. And then we're going to have log to the base 2. We're going to have 2 to the power 3p. Yeah, because remember the rule, am is the same as a to the power of m times n, which is amn. So here we have log to the base 2, 2 to the power 3p, and then we are multiplying it by 4 to the power of q. Now we can simplify what is inside. This is 2. The common factor is 2, so we can rewrite this as log to the base 2, 2 to the power 3p, multiplied by 2 to the power 2. Yes, 2 to the power 2, and then we have our q at the back there. All right, so we are going to have, I'm transitioning so we can continue from some different angle. Yeah, so now we're going to have our log to the base 2, and you have 2 to the power 3p multiplied by 2 to the power 2q. Can you see that? I hope you do. You have log to the base 2, and then the bases are the same, and they are multiplying. So we add the exponents. We are going to have 2 to the power 3p plus 2q, I believe. Now we're going to have log to the base 2, 2 to the power 3p plus 2q. Now remember, the rule is, we said that if we have log 10n, we said that it's n log 10. We drop the n. So here too the same thing. we're going to have 3p plus 2q. It will drop, and then we're going to have log 2 to the base 2 to the base 2. Now, remember we said that if you have log a to the base a is 1, they're the same. So that this log 2 to the base 2 is 1, and then it's going to be multiplied by 3p 3p plus 2q, and they are multiplying. So the answer is 3p plus 2q. So we've been able to solve from the left hand side to prove the right hand side. Able to solve from the left to prove the right hand side. I hope this particular video helped. Please, if you haven't yet subscribed to our channel, please do us a favor by subscribing, please, so we can grow this family together. In today's lecture, we're able to look at indices and logarithms in a very complete manner. But before I go quickly, let me just drop this gem. If you have any log to the base e of x is the same as ln x, you see them on your calculators. It means logarithm to the base e. Whenever the base is e, it's a ln. Whenever the base is 10, you don't have to write it. So if we want to write log maybe 3 to the base 10, we don't have to. It's just log 3. It's just log 3. If we say ln 4, we mean log to the base e of 4. If we say ln 100, we are saying that it is log 100 to the base e. That's all we are saying. So I'll end here. I'll come to you another time. Take care and bye.